Welcome to this video in which we work an example of nodal analysis with a dependent voltage source. In some ways this is about as bad as it gets with nodal analysis, and you'll discover that hopefully it's not that bad. So our goal is to find all the node voltages associated with this circuit. So let's go ahead and do nodal analysis. Because we have a dependent voltage source, things will get a little interesting, but they won't be that bad. Okay, so the first thing we want to do is define a reference node, and I'll define this node at the bottom to be the reference node. It's not the only one that I could define. In fact, if I wanted to save myself some trouble, which I don't because I want to illustrate a point, I could define this node over here to be the reference node, and it would actually make things a little easier. But since I'm more interested in showing how to do this for the hard case than making it easier, I won't. The next thing we need to do is determine what the node voltages are. So we have a node here. We'll label this node voltage V1. We have a node here. We'll label this V2. And we have a third node here. And we'll label this guy, whoops, something incomprehensible. We'll label it V3. Okay, so how do we proceed to do nodal analysis? Well, we'd like to start with node 1. But you'll notice that node 1 is connected with a voltage source, this 5Vx. It's a dependent voltage source, but it's still a voltage source, to node 3. So this kind of complicates things. It turns out that we know what we need to do, though, to make it work. First off, we know that because of the voltage source between node 1 and node 3, that V1 minus V3 will be 5 times Vx. Now I'm going to simplify things a little bit here. Vx is the voltage across the 4 ohm resistor, but you'll notice that that's actually V2. So rather than write Vx throughout the rest of this, I'm going to call this V2, because it will make it easier when we go to actually solve the system of equations. So that's one relationship between the voltage at node 3 and node 1 that we can get. We still need to get another equation from node 1 and node 3, and the way we will do this is by defining a supernode, which again we do when we have a voltage source between two nodes. So here's the supernode. Okay, and what we'll do is apply Kirchhoff's current law to the supernode, and we'll basically say, how about the sum of currents entering the node is equal to the sum of currents leaving. And again, we're talking now about the currents that are entering or leaving the supernode, not just node 1 or node 3, but any current that's entering or leaving node 1 and any current that's entering or leaving node 3. That's the whole idea behind a supernode. So when we do that, we can find then that we have a current through the 2 ohm resistor, and that current will be V1 minus V2. That's the voltage across the 2 ohm resistor divided by 2 ohms. So that's basically the current going this way. And then we'd have the current going through the 1 ohm resistor, which will be V3 minus V2 over 1 ohm. So that's the current going this way. We then have the current going through the 3 ohm resistor. That'll be V3 divided by 3 ohms. And this will be equal to the current coming into the node, which is this 3 amps. Okay, so that's a second equation that we got from nodes 1 and 3 by considering them a supernode and applying KVL at that supernode. And I can simplify this a little bit as V1 times 1 over 2 ohms minus V2 1 over 2 ohms plus 1 over 1 ohm plus V3 1 over 3 ohms, and this is equal to 3 amps. Okay, so now I have two equations that I've gotten from nodes 1 and 3, so that's basically all I can hope for. I still need to get an equation from node 2. Now node 2 is just a normal standard node, and so we can write down its equation by inspection. We have minus V1 times 1 over 2 ohms plus V2 1 over 2 ohms plus 1 over 4 ohms plus 1 over 1 ohm minus V3, and that would be 1 over 1 ohm, is equal to 0. Okay, so I think we actually have everything we need to be able to plug this into our favorite equation solver, which again right now for me is Wolfram Alpha. So let's go to Wolfram Alpha, bring up a clean window with this really funny looking red pattern, and type in our equations. We have V1 minus V3 is equal to 5 times V2. V1 times 1 over 2 ohms minus V2 times 1 over 2 ohms plus 1 over 1 ohms plus V3 times 1 over 3 ohms plus 1 over 1 ohm, and this is equal to 3 amps. And finally, minus V1 times 1 over 2 ohms plus V2 1 over 2 ohms plus 1 over 4 ohms plus 1 over 1 ohm minus V3 times 1 over 1 ohm, and that's equal to 0. So hopefully if we got this right, we just hit return, and Wolfram Alpha does a lot of solving for us, and there you have it. We end up with V1 equal to 162 volts, V2 is 36 volts, and V3 is minus 18 volts. So that wasn't so bad, was it? So we can go back and label these nodes then. We have V1 was 162 volts. We have V2, which is the same as Vx, equal to 36 volts. And V3 is minus 18 volts. So there you have it. We've done nodal analysis on a fairly complicated circuit. Complicated in the sense that it had a dependent voltage source that was not connected to the reference node. This pretty much finishes this example. We'll see you later.